like we can ask our LLM obviously questions and do so, through OpenAI's API. But it doesn't have up to date information. It doesn't have necessarily curated information. We have no way of validating that information that it's using. So instead, the technique oftentimes is we can provide it essentially with context. Okay. So the first way that we did that was, when a query comes in, we use just the Google News API to then find the relevant news articles, right? And then, we pulled out some text from them, and then we gave that text to our LLM, right? So we just updated the question to say, hey, with the context below, please answer, whether the movie Barbie was nominated for an Oscar, right? And then it will use this corresponding information to answer the question. But for a production grade application, that's not something you're going to do. I mean, one, you have to wait and rely on this external data, which you're not going to want to do. Two, right, kind of as we mentioned, you don't know the validity of that data, right? You don't want to be using inaccurate data and giving back responses based on that. Three, some of the data could be, probably your proprietary information. So that could be, say, like IP that you've generated or that you have. It could be private, like company information or documents that you just want, internally available or you want people to pay for, things like that, right? So instead, what we'll do, both for because we want to validate our data, both because that data might be proprietary. Instead of reaching for an outside resource and just pulling it from the web, what instead we'll do, of course, is store the data in a database. Okay. So here you can see the question comes in, and instead of going to the web, right, we use the vector database. And we'll talk about why it's a vector database in a little bit, as our data storage. But then the rest is the same, right? What we'll do is we'll find the most relevant documents from the vector store, and then that will be presented to the LLM. So that part's really the same, right? We find the most relevant piece of information from our database instead of asking Google to do that for us. So how does something like that happen? I mean, this is where it can get tricky. Essentially, it's two different stages. One is all the information that we want to store, we'll put that, we'll need to embed that, meaning we'll need to turn it into a series of numbers. So let me just show you, we can kind of show you how this works. So here we have, I think this is my up-to-date API key. So here you can see, I have my OpenAI API key. The model, right? There's different trained models, and then each of them will produce what we'll see is a different embedding. And then what I'm doing is I'm taking my list of inputs. So you can imagine that each of these are different news articles or whatever, right? But essentially they're different documents at this point. But these are my different inputs, and then I'm specifying that I want this model to then create embeddings from them. Okay? So this RES data is going to be a list of, I call them vectors lots of times, because by vector I just mean it's a Python list. Really, it's a NumPy array. And as you'll see, there's a set of numbers for them. And then I just make sure that we do, in fact, convert them into a NumPy array, and then I store it on a data frame. And you can see that here. So let's just take a look at this. This is taking a second because it is hitting the API. And if you look at let's take a look at the embeddings. Okay, so this is the embeddings. I also want to, let's look at the DF, the data frame. Okay, so here's the word, tree. And then what you can see is it translated into this embedding. If you look at this thing, so we have df dot embedding. You can see, df, let's do dot iloc 0. 0 dot embedding. right? You can see this is a NumPy array. Okay, and if you look at the length of this thing, by the way, right, it's 1,000. So just the word tree is encoded, right, in 1,536 different values. So the length of this array is 1536. Okay, each, regardless of kind of how long this is, if we had more than just a single word, but let's say you could have even like 2,000 words, it would embed this into an array of this same length. Okay, and so each word gets it, but it has an algorithm for basically translating text into and representing it as an embedding or as a vector. Okay. In terms of how that's done, there's different, like typically, really, and probably a lot of you know this, the way that that's done is by trying to simply predict what word comes next. There are other techniques other than that, but essentially they're a variation of that. But the main thing I think to know is that, this vector has 1536, and that's called they'll call that like dimensions. But imagine if it just had 3 dimensions, So what you can imagine is, if we have 3-dimensional space here, this way, okay, and then we have a vector, and let's say we want to represent it. My art skills suck. But right, let's say it's coming out 1 and then up, right, and then so it's coming out here somewhere. This 3-dimensional space, meaning, okay, it has x, y, and z coordinates, right, as like 0.5, 0.8, and 0.3. That's what our text is ultimately going to be translated into. And what you can imagine is that, say we have the word, king, okay? Well, if the first dimension is for, say, like gender, the second dimension is, say, for like the period that is, that's represented with, like the time period. And then maybe the third one is like status, okay? Then you can, gender, let's say like it's a 1 for male. Time period is like, let's say it's 0.4 because it's like the 1500s or something like that. That's typically associated with. And then the status, let's say that's also pretty high, because, king obviously is high status. So then that would also be, right, like 0.9. And maybe that's, that represents just like to the max. All right. Now, you can imagine then that this can become pretty useful in like comparing words, right? Because if this is king, right? And basically we're going to want to ask a question like, who is the most powerful person or the most powerful, male figure in the data set? Well, then, if it knows that, male obviously is translating to this kind of axis, right? Or if it wants to embed this entire vector and it sees, the word powerful and male, you can think that all this text will also translate to something pretty close to king in terms of gender, pretty close to king in terms of, power, right? We don't have a time period thing, so maybe that one's left ambiguous or like neutral, but the rest are pretty good. Another thing that kind of occurs is you can imagine, right, if we have the word queen, let's do that. Well, then everything's going to be pretty similar with queen, except the gender might be 0, right? But the time period is also 1500s. And here the status would also be very high, right? So you can see that if we're comparing king and queen, you would expect that these vectors would be pretty similar in terms of just like the values that they have. Now, so if we have 0.5, 0.4, and 0.9 or for king, then you would imagine, right, we would be drawing a pretty similar vector for queen. Basically, the dimensions would be exactly they would be exactly the same, except for, maybe one of the dimensions. So then if you compared these two things, meaning if you try to like assess the distance between them, they would be pretty close together. All right? It's the same thing with this. If you tried to assess the distance of, say, these words that now have, something like powerful and male with each one of these vectors, right? The one related to king is probably going to be pretty similar. So what we'll do, and what you can kind of see, is the first step is to take everything, let's say this was, this is our database, this is our set of documents that we want to then feed to the LLM, right? When we want to feed it relevant information, the first thing that we'll do is embed each of these into a separate embedding, right, or vector. And then the second thing that we'll do is when a question comes in, that will produce its own vector, right? So create another, vector, and then we will compare the distance between the two, between the question and the related document. So you can kind of see that, like let's say, oh sorry, I'm doing the wrong one. Okay. So let's say, this is king, this vector represents king, this vector represents, queen, and then we have another one that represents the text like bagel, that's like way over here. If we were to compare, king and queen, or let's say something like this query vector, so we, step one would be embed all our documents. So we translate them all into vectors. Okay, so you can imagine that even though it's numbers, everything's a number, everything's a separate vector, you can imagine that each one of these represents a different document. Step two is then compare the query, right? Someone asks a question, compare the query with each one of these different vectors. Okay? So step two is someone puts in a query, we'll convert that query to its own vector, and then we'll compare the query vector to every one of these vectors that we already, calculated. All right? So if someone asks the question, who's the most powerful male figure, then that will be compared against every one of these. How will that occur? Right? The query vector gets turned into a vector. So let's say that thing looks like this. And then what you can imagine is just comparing the angle between the query vector and each document. So this one's going to be very small. This one, here the query vector versus this one will be a bit larger, right? This represents the queen. And here the query vector versus like the word bagel, right, will be larger than that. This is, there's different scores that you can do, but this is like the cosine, right? So the cosine is just a way to represent the distance between these different vectors. All right. So what we'll do is you just return, the query comes in, you'll find the three closest vectors by calculating the cosine score between the query vector and every document, return the closest three, those vectors with the smallest score, and then take those three vectors along with the text and send them to the LLM. So you can see that's what we're doing here. Step one, right? We embed each of our documents by feeding them, just in this case, just feed it to the API. Step two, we'll then get a query vector, get the embedding from that. Step three, we'll go through all of our embeddings, all of our documents, and compare the distance or calculate the distance between the query vector and all of the existing documents. Here I just added a new attribute called distances, and then finally we can sort, just choose those words or documents with the smallest values that are closest to the query vector. So let's take a look at that. We can kind of, if we run this, we can then take a look at each of this. Okay. So if we look at our, you can see if we look at our data frame, so this is essentially representing our database. You see we have embedded each one of these pieces of text, right? Tree is this, Bagel is that. King is that. Then the next thing we did was we also took our query vector, and that represents its own thing. If you look at it, like, you can just kind of, this is the word king, right? That's what we're embedding. So obviously if we compare king with king, right, they look exactly the same. And then if we use, the cosine of, let's just get back king. So df, I can do it this way. Here's my list of embeddings. We'll just get the third one. I think that's the one representing king, right? And then we calculate the cosine of the Q embedding array, which came from embedding it here, with, sorry about that. Yeah, with this embedding at 3, we should see that it's, oh, did it not return it? Oh, I did 2 cosines, I'm sorry, gang. I may have to redo this. Yeah, let's do it one more time. Okay, we can see that it's 0, right? Because the distance between the array, those 2 vectors are perfectly overlapping. So there's no distance between them. If we ever look at it with a different one, like for instance, let's do it with queen. Let's take a look at this df again. We'll do df queen is number 4 dot iloc 4 dot embedding, right? We'll pull that out. And now let's just do with number 4, this is 0.27. Let's try the other one. Let's do like bagel, right? And here you see it's a lot larger, 0.76. Okay? So what will we do? You calculate all the distances in my df, and then finally do df.sort values by the distances. I probably should call it distance. Distances, that should give it to me descending. Then just choose the top 3, right? So these are my 3 closest, king, queen, and prince. That makes sense. And then this is what you'll feed to the LLM, right? You'll pull out the text. And now this will be essentially text.values to get the list. And then maybe we can join it. Can I do that? Yeah, pretty close, right? So we can now send the top 3 documents as the context to my LLM. All right? So that's the idea. So then what's the last? You take this context, and then you can see I have this utils thing, and basically what we're doing is you can get the context, the prompt, right, from utils, generate prompt, import generate prompt both from the question that we get in there and from the resulting context, which is the top 3 documents, right? And then this prompt just says, based on this context, answer the question, and then feed that to the LLM. So let me see. If the question were most powerful, instead of who is the most powerful male in the data set, would that alter the chances of matching with different results according to distance? Confused whether the LLM understands the sentence semantically and then converts the embedding accordingly. I don't know, Conway, you may have to jump in here. I don't know what you mean by first understanding the sentence semantically.
Yeah, I'm a bit confused about the role of this whole sentence. So I totally understand how the embedding possibly works when it comes to single word like tree, given and so on. I'm a bit confused for the question part, the embedding, how the embedding exactly happens for the whole question, like when you said who's the most powerful male in the data set. So I was curious, what significance does this data set play in that regard? The who is the part in that regard?
I see. What you'd really do is, so the question I think is like, how do we control that it will be, from the data set? What you typically, this is more in the prompt. that you can make sure that is based on the context, right? So in the prompt, you can say something like, provide a 2 to 3 sentence answer to the question based on the following sources or based on the following prompt, right? And then here I say, like, be original, concise, accurate, helpful. Then you provide the question, and then you can specify, put, here you can use that word properly, like prompt, and then provide it here. Or you can just change this to context. In the LLM, like in my experience, is very good at then just using the information here, right? So Conwell's question is like, if you say who's the most powerful, figure, how does it know you don't mean like in the planet, just like from its general knowledge, as opposed to using the prompt? But typically what you'll do is in the prompt, you'll say, based on the context, something like that. And then the LLM is very good at only using that information. And you'll see that when you play around with this in the lab. I think you'll see that. Yeah, Narapati.
Yeah, so I saw you show that one word and then it's get vectorized to 115.76 of like
Mm-hmm.
length.
Mm-hmm.
So I'm wondering if like the whole sentence will be the length of the vector will be the same size.
Yes, it will. So for the way that like a neural network works, like basically it can't really it just, if you kind of think about it, it's hard to I guess it's hard to explain without getting too deeply into how a neural network works. But like the length when you make a prediction, when you try to feed it an input, it's almost like you're passing through a function to it. So you would call predict. The dimensions of this have to be consistent for it to work. So for it to work, for it to get this function, for you to pass something through to ChatGPT, the length of the vector always has to be the same. So obviously, so if you just think about how ChatGPT works, we can provide various lengths, but then when text of various lengths, but then when we ultimately feed it into ChatGPT, it has to be of the same length. It has to be the vector size is the same. So if it doesn't know certain things, like let's say we just have the word, like bagel or whatever, and it's like, well, how powerful is a bagel? It'll have 0.5. It'll have some neutral value that is just not so sure about when it gets to that dimension, right? And then when it gets to something about like food or tastiness or whatever, right? Like it'll be much more strong, okay? And so you'll get a bunch of neutral values for like power. These will basically not have so much influence when we're retrieving and we say like, okay, tell me like tasty food. Again, this text will also have like pretty high values here, okay? And so here will be good, right? But on this third dimension, this will just not play too much of an influence in retrieving it. Okay. What's interesting about this, and what's kind of cool about it, is this is a reason why this vectorization is a reason why LLMs are very good at translating. They're exceptionally good at translating. They're really good at, and the fact that was like one of the first use cases for ML in general was, if you think of like how Google Translate works, was that they're also very good at like antonyms. So you can do something like with an LLM and say, a king, and this is like the typical example is like king minus maleness, right? And you can, in some libraries, allow you to do this. You can do like king but not male. You can imagine wording it like this, and it will then be able to predict queen. How does it do something like that? Well, if you just think of like we vectorize king as strong for power, male, and ancient, like time period, and then we do queen. Basically what you're doing for this one is, while this is going to be the same, so this will be 0.8, this will be 1, and let's say this is also 1, and then this is power is also the same, but now this is 0, and now this is the same as 1, what you're telling it to do is king, same vector, but subtract the value, subtract maleness from the king vector. So it knows just flip this, just -1 here, and what will it get? It will get back queen, right? So that's why, and you can start to see then how LLMs become very good at understanding your text too, right? Because it can kind of pick up this context and be like, all right, we're talking about this attribute. Let's see what we get if we have this thing, but not this component of it, right?
So,
If you say king, but for the United States, right? Now time period all of a sudden would probably shift to something else.
okay, Joe, one more question. So let's say we have two sentences, right? And then in those two sentences, there's no similar or overlap terms, but they're very similar semantically. That means when we embed it, the vector will be very close to each other, even though we don't have the same term in each sentence.
Well, probably on this, if there's a semantic scale, like semantic dimensions, right? That will be similar, but not right, but not the subject matter, right? So that's why you could do something like, write the Constitution as if it were some sort of whatever pop star lyric, right? So that's just taking the subject matter, and you can imagine the subject matter is over here, but then the semantics of it, right, the style is in a different set of dimensions. Something like that. Yeah, so for that, right, you just have to imagine like right, we get 1,536 different dimensions. So we can keep it, with like powerful, power, whatever, but now describe, the president or the king in terms of like a director or whatever. So, it's able to then that's a little trickier of an example, but it's able to kind of keep these attributes and translate, have a different context for work. So what does it mean to have a king in this arena, right? If you translate that to, if you think about our vector, sorry, I did the wrong sharing. If it's like, what can I share? Okay, if you think about like a king, but now like in the film set, right? Maybe that's a director or the top actor or actress, right? Like you can imagine that now this part, the powerful part, is all the same, right? But now it's in a different kind of arena. So still higher on the power level, but now we're in the movie set world. What does that translate to? And it's like director, right? So the director would be over here. Okay. So it's just kind of like certain attributes are the same, but changing the dimension would put it in a different spot. So these words are, and you have to imagine that each of these words are embedded properly, are properly mapped out, right? They properly live on the map or when you embed them. So then when the query vector comes in, it basically searches through the map to figure out, okay, like what should it be retrieving? Cool. The readings are helpful. I think, it is hard to embed, it's hard to imagine something in 1,500 dimensions. But I mean, one thing to think about is like, here we're talking about like 4, like I think like a powerful male figure from a certain time period. Right, where you can imagine, right? That's like 1, 2, like 3, 4 dimensions, and already you can capture, a certain degree of information, right? And then you can imagine going down the list, right? Prince, then we don't need to really represent it with any more than still only 4 dimensions. Just turn down the dial a little bit, right? Princess, right? Same 4 dimensions. Just change the dial a little bit, right, on gender. So you can start to just see like how powerful something like that is. would you say this director vector is orthogonal to the king vector, which means no? So you know, which it means that there's no similarity. So this is kind of like getting into matrix algebra or geometry. So orthogonal is just a fancy word for perpendicular. It's a little, just for the time being. So this is kind of perpendicular. But if you imagine it, and this is where the geometry kind of makes it a little harder, but you just have to imagine that if we have a director vector, and then we have a king vector, right? They're gonna in a lot of dimensions they're gonna be pretty similar, right? In terms of power, they're gonna be high up there for their realm. In terms of, I don't know, control, or I don't want to get too weird about it. So right, they're both typically male, right? We can put that high up there. So, and now we calculate the distance, the distance between them. One way to do that is simply just subtract them, right? If you want to get fancier than that, first convert them to absolute value. Subtraction actually works fine. Meaning you subtract this from this and you get 0, right? So they have no difference in the power scale. Let's say they have basically no difference in the maleness scale, right? And then they do have a severe difference in something else. So what will they, it's able to see that, hey, is prince similar to, what's closer, king, prince, and director? Well, prince is closer, but director's pretty good. And remember, we would have that whole thing of what's a king in the context of a movie set, right? So it's like, it would be something like, here's king, here's director, and then when we say in the context of a movie set, you would have to imagine that now we're adding on the movie set quality. So that's going to nudge this. All right? Could you embed larger text? For example, this is a good question. Could you embed a larger text? For example, could you embed an entire book so that you would get similar values that have similar stories, readings, genre level, etc.? Okay, this is an excellent question. So it's like, what's the size of text that can be embedded? And there's different things there's kind of different problems, right? So one is, we have to reduce it. You're compressing, right? This is essentially a compression problem, where you have a lot of text, and let's say it's like 20,000 words is a book. Well, now each word, when I just have the word king, right? We have a single word is getting 1,500 values, whereas in this case, 20,000. In this case, we have 20,000 words is getting 1,500, also only getting 1,500 values, right? So, the entire we're going to be losing a lot of information. So, what is like a typical size? Maybe that's a better question. A very small embedding is like 200 words. Okay, so a paragraph. Okay? A good sized one is around like 2,000, 2 to 3,000. So what would that be? That's 4 or 5 pages, I guess, right? Like if you think about just your typical essay, right? So a good size one is going to be like 2 to 3,000. Something that you will play with. Basically, what we'll get into is, this is called chunking, all right? And that is like a parameter. How do you know what's the right chunk size for your document? You experiment, right? You experiment. I'll send out a reading that gives more information than that, like more rules of thumbs. But a typical thing is just like, okay, I have this book. How large should I break this up into and then embed, right? And a good way to find out is, 1, from other people's past experiences, but 2, to literally try different chunk sizes and then test it out and see how good a job does it do at answering the questions. Are embeddings related to a context window? I'd say chunk size is. So context window, at least the way I understand it, is the context window is what we feed to the LLM. Okay? So let's just, let me show this. So if you think about our RAG pipeline in general, right, we're going to, take a bunch of documents, okay? Then what we're going to do is chunk them up. So let's say we take a book or a PDF. Then what we'll do is we'll chunk them up. Maybe I'm getting a little ahead of myself. So you can imagine putting this into different chunks, right? Each one, let's say, being a paragraph, if it's chunk size of like 200 words. Then we vectorize each one of these, right? So each one of these turns into a vector, all of the same length. Right? All of a vector of length 1536. Then the question comes in, who wrote the movie or who directed Titanic? Right? It will pull out the top 3 results, calculate the distance between this and every vector in the database if things are simple. And then what happens? Then we'll take these 3 documents, combine them, we can put like a little, demarcator between each one is fine. And then we'll send that to the LLM. The LLM will then, interpret that text to give you back an answer. So this part, you can think about the answer, like feeding the documents to the answer as the response, kind of like, I forget if it's called like response or like response synthesis, something like that. This is what I think of as like the context window. The context window is how much information, like how much text can I feed to an LLM to the point that it still understands it, right? If I feed it, too much, it doesn't know what to pay attention to in your context. So, right, like if you can imagine feeding it like a bunch of different tweets, the more unrelated those tweets are, the less it knows what to pay attention to in interpreting your text. If you feed it just more information in general, right, then it will run into similar problems where it doesn't know what of that information to pay attention to. So where context window comes into play here is, well, why not just feed it back the entire data set, right? Because of a context window, because it has limitations, it doesn't perform as well when you provide too much information that then it has to figure out what to pay attention to in that information, right? That's more what I think of context window as coming in this stage in terms of it then synthesizing results from what it's shown. Okay, does that make sense? So what we're doing, right? We embed it. The query comes in. We pull out the top 3 results. These results, these that we're going to send to the LLM, those are my context. Okay, and then the context window is what can the LLM feasibly pay attention to and interpret. It won't just give up, but it will do worse, right, at identifying the correct information there. Right. So that is something in terms of like the size of information you want to give back to it, right? That would depend on things that are a factor of that. It would be 1, the number of documents you send back, or / maybe we could use the word chunks you send back, and then the size of each chunk. Okay. But these are again like parameters that you can experiment with, right? To see how well your model performs at then giving the right answer. All right. So this is, this is a lot of ground. But I think the questions I'm getting are really good. As long as you kind of understand that you'll start with a document, and we'll move through these, right? You'll chunk it. Even that part we didn't officially get to, the chunking. Then what we'll do is once we have this document separated into different components, all you'll need to do is just turn it into vectors, right? So each one turns into a separate vector. Then, these vectors are stored in your database. And that's kind of step 1 is done, right? This is like storage. Step 2 is then retrieval, right? Where someone will ask a question. This is like, same thing with a normal database, right? We load the data in, and then at a later point we'll query the database. So step 2 is then retrieval, right? This is where a query comes in. Remember, the query first has to be converted to its own vector, and then we'll perform some sort of similarity search to pull out the 3 closest vectors, right? And then send the text to the LLM for it to give an answer. Will we have a hands-on lab that processes documents and loads it to a vector database? Yes. So we'll do that. First, we'll use our own database. Then we'll move to using Llama Index and show you how to do that with that. All right? Cool. All right. Any other questions? No? All right. I mean, these were really good questions.